Hey guys, so in case you're wondering, I am going to eventually have all the lectures from on magnetism from before spring break posted, but I just really want to right now make sure the current lectures are also being updated on YouTube as to go along with the course. So I might have a few lectures missing in the middle, but they will be up very soon. So today is I am continuing with new material, and I am going to be the big topic of today is Ampere's law. And so, what is Ampere's law? And well, right now I am showing you this picture. So what we have is we have a slide that demonstrates the relationship between the direction of electric current in a long straight wire and the direction of the magnetic field created by that current. So to know the direction of the electric current, I align my thumb on my right hand with the direction of the current, and then I wrap my fingers in a certain direction. And in this picture, the current is flowing straight up, and so the fingers will wrap in this way around the wire. So this is the direction of the magnetic field. This is using the right hand rule. Now, I will say take a moment, be comfortable with this idea. I'm going to show you the example problems from the next slide because this is going to be important when we talk about the notion of Ampere's law. So if I have a current that is coming towards me out of the computer screen, I take my right hand, make sure you're using your right hand, not your left hand. It's silly, but it is a common mistake people make. So have the thumb of your right hand pointing towards you. You notice that your four fingers are wrapping in a counterclockwise direction. Now, really, to describe magnetic fields, we need 3D. We can't have magnetic fields in 2D. So what if we have the current flowing to the left? Well, now I want the thumb of my right hand flowing to the left. And if my fingers are above my thumb, they are pointing into this computer screen. If my fingers are below my thumb, they are pointing out of the computer screen. If my fingers are behind the thumb, they'll be pointing downward. If my four fingers are in front of my thumb, they will be pointing upward. That was way too many words beginning with f sound. So this is the right-hand rule for determining the direction of the magnetic field created by a long straight wire. So what are we actually going to do with this to talk about Ampere's law? So for Ampere's law, also I will tell you, in my opinion, Ampere's law is one of the most abstract concepts we're going to talk about in this course. It is something that we need to get through. It doesn't need to be too bad. So it is one of the more abstract things. So if you struggle with it at first, I don't want you to feel bad. That is very normal. Reach out to me, come to office hours. I will talk with you. I will help guide you along. Reach out to me and I will make sure you understand it. So what is Ampere's law? To describe Ampere's law, we're going to talk about two vectors. One vector is going to be the magnetic field created by a wire. So as a first simple example, let's have a long straight wire. Based on how I drew this picture, we have the wire has current flowing into the page. So, okay, we have current flowing into the page. If I use the right hand rule, thumb of my right hand is pointing into the page, and I notice my four fingers wrap around that wire in a clockwise direction. Now, the magnetic field is created by this current. The magnetic field exists at every location in the universe. So everywhere on the computer screen, there is a magnetic field vector at that location. Now, if I'm close to the wire, I'll have a really strong magnetic field. If I'm far away, I have a weak magnetic field, but I do have a magnetic field at every location. Okay. Now, let us travel in a closed loop around the wire. By saying let us travel, what I mean is you're going to pretend you are somewhere away from the wire, and you are going to physically walk around that wire. Now, when you walk around a wire, well, you need to take a certain number of steps along the wire. So if you think about what is a step, well, a step will have a certain length, and your step will be directed in a certain direction. So a step has a length and a direction. I could think of a step as a vector. So we will be comparing two different vectors in this example. One vector is the magnetic field that exists everywhere, that is created due to the current in the wire. The other vector we're going to consider is the path we take by many, many steps. Each step has a size, length, and a direction. So if you stop and think about it for a moment, you could convince yourself that if you are walking in a path around the wire, you have two possibilities. You could either travel in a clockwise direction around the wire, or you could travel in a counterclockwise direction around the wire. There is no other possibility. Even if you do some weird loopy path like what I have drawn here, technically this path is, I will say, on average in a clockwise direction. So I'm going to write an equation. The equation will have my two vectors, the strength of the magnetic field and the step I take. And I'm going to make a really large sum, where that really large sum is the strength of the magnetic field times the size of the step I take, times the angle between the direction of the magnetic field and the direction of my step. And I'm going to add up every step along my closed path. So on this slide, I intentionally made my path in an arbitrary shape. Later on, when we really use Ampere's law to perform a calculation, the shape of the path we take will be more carefully chosen. But right now, I want you to think more in the abstract, more just conceptually. The path I take will either be, on average, with the magnetic field or against the magnetic field. The path will be with the magnetic field if I go clockwise, against the magnetic field if I go counterclockwise, assuming the current is flowing into the page. If I chose to have the current coming out of the page, that would reverse the direction of the magnetic field. But the important take-home message, your path is either going to be with the magnetic field or against the magnetic field. There's no other possible option. So, what are we doing here? Well, pick one step along the way. So maybe I'll pick this step right here. So here's my step I take, and here's the magnetic field at the location of my step. At that step, I have a certain strength of B, a certain strength of magnetic field. I have a certain size of my step. Okay, my step is that big. And I have a certain angle between the direction of B and the direction of my step. And that angle is theta, this angle right here. So what I want you to do is I want you to pause the video, convince yourself that in this picture as is drawn, the sum of every step along this path of B delta L cosine theta must be bigger than 0. Now, I'm not claiming it will be a huge number or a small number, but it will be a positive number. It might be 0.001 or it might be a googolplex. But whatever, if your path is in the same around the wire, is in the same direction on average as the magnetic field, convince yourself this entire sum should be a positive number. So pause the video, convince yourself this is true, and I will be back in a moment. Okay, great. So you convinced yourself this is true. What I'm going to do now is I am going to just take this equation and I'm going to rewrite it a little bit, make it a little easier to work with. So here is a picture of a very particular step. So here is my step I take that's going straight up towards the top of the page. Here is the magnetic field that, based on this, is kind of up and to the left. So there is an angle between the direction of the magnetic field and the direction of my step. Now, here my step is more or less parallel with the direction of the magnetic field, so that would be an angle of 0. Down here, it looks like my step is perpendicular to the magnetic field, so that'd be an angle of 90. If I want, I could say this term right here, this term will be b cosine theta, because I could think of this as the projection of the magnetic field on the step I take. Mathematically, that is a valid way to think about it, but you could just use simple trigonometry and things we learned about in chapter 3 to convince you b cosine theta will be this large. So here's a b cosine theta, here's a cosine theta. I'm just going to call b cosine theta b parallel. So b parallel is the component of the magnetic field that is parallel with the direction of my step. Now, if I want, I could write this sum up here as b parallel times the step length. And instead of saying I'm summing over every step, I'm just going to say I'm summing over a closed loop. So take a moment, convince yourself that this term down here is the exact same thing as this term here. I'm only rewriting the terms I'm working with. I'm not actually changing anything. Okay, so we said B parallel L must be bigger than 0, and we argued that because that must be true because on average, our path we drew is in the same direction as the magnetic field. So this term must be bigger than 0. If our path that we chose happened to be drawn the other way, where we were walking counterclockwise around the wire, then it would be a negative. That summation should be a negative number. So it's going to be bigger than 0. Now, what is it going to be? Well, I'm going to pause the video and you'll have to find out in the next video.